When a vehicle hits a barrier at highway speeds, the physical reality is chaotic. Metal folds, tears, and buckles in fractions of a second. To simulate this event accurately, engineers rely on explicit finite element analysis. This method requires slicing the crash into incredibly tiny fractions of a second, microscopic time steps, ensuring the mathematics do not spiral out of control. At every single microstep, the software calculates variables for each node: displacement, velocity, acceleration, stress, and strain. If we isolate one node for one time step, this highly efficient calculation finishes almost instantly. However, this incredible efficiency introduces a paradox. If the underlying equations are so light, running these simulations should not push high-performance hardware to its absolute breaking point. The actual compute load comes from sheer volume. That lightweight calculation is multiplied across a physical mesh of millions of individual elements, and then recalculated over millions of consecutive time steps. A single step is light, but the aggregate total is crushing. Managing this volume requires splitting the work. Engineers deploy massive parallelization across specialized, highly tuned Linux computing clusters just to process the sheer quantity of operations. Software like LS-DYNA transforms structural mechanics into a massive information engineering problem, where the physical outcome depends as much on high-performance computing efficiency as it does on material science. To handle this immense mathematical load, software engineers map the physical geometry of the vehicle directly onto the architecture of the computer processing it. Through domain decomposition, the vehicle's physical mesh is fractured into localized blocks. This distributes the workload. Thousands of elements are grouped and assigned to a single CPU core. Each section of the car is directly wired to a specific processor. In theory, this leads to a straightforward assumption about linear scaling. If you double the number of processors, the simulation should finish in exactly half the time. The reality of parallel computing is far more restrictive. Doubling your core count rarely results in a direct doubling of speed in dynamic physics environments. The first degradation in efficiency is communication cost. Cores cannot operate in total isolation. They must constantly pause calculations to exchange data about what is happening at their boundaries. Then there is the friction of load balancing. If a severe impact hits the front bumper, the core processing that zone becomes bogged down with complex calculations. Meanwhile, cores assigned to the undamaged rear finish early and sit completely idle, waiting for the active core to catch up. Adding more processors yields diminishing returns because every part of the simulation must remain strictly synchronized, both chronologically in time and physically in space. We have to look past the processing units themselves and focus on the physical data pathways connecting those cores to the system's memory. Consider the exact boundary where two core domains intersect. During an impact, these sections violently deform and physically overlap. Calculating this cross-boundary collision requires an instantaneous exchange of nodal coordinates, contact forces, and material states. This creates a severe hardware limitation known as memory bandwidth. Modern multi-core CPUs are incredibly fast, but they process the math faster than system RAM can physically feed them. This delay in delivering updated coordinates and stress states creates a massive traffic jam at the memory bus. This bandwidth choke point is further compounded by heavy I/O operations. The system is continuously writing gigantic result files to storage, demanding even more capacity from those pathways. A standard workstation with 64 gigabytes of RAM is perfectly adequate for learning or reviewing small components, but a full vehicle crash demands specialized server architectures designed to provide immense memory bandwidth. The ceiling for explicit solvers is ultimately set by how quickly the motherboard architecture can move data, rather than how fast the processor can calculate. All of these hardware limits converge on the single most computationally expensive phase of any explicit simulation, the contact search algorithm. When structures buckle, the metal folds over onto itself in unpredictable patterns, creating hundreds of new physical intersections. The contact algorithm has to track this chaos. At every microsecond, the software must determine if any given node is penetrating any given face across the entire vehicle. Checking every node against every face is impossible. Instead, the solver builds dynamic bounding boxes to isolate clusters of nodes nearing collision. As elements crush and are deleted, the software continuously rebuilds these spatial trees to track the chaos. Given this heavy reliance on parallel tracking, you might ask the logical hardware question: why not use GPUs, which offer thousands of parallel cores designed for geometric math? GPU architecture relies on SIMD processing. This makes GPUs highly efficient for uniform, predictable workloads. But crash physics are the exact opposite of uniform. Complex branching logic, erratic memory access, and continuous element deletion completely shatter GPU efficiency. The wildly unpredictable nature of spatial contact search mandates the flexibility of high-frequency, multi-core CPUs. They remain the core requirement for solving dynamic structural collisions. After the hardware has executed the calculations and generated the massive result files, the burden shifts to the end user, the CAE reviewer analyzing the completed run. Here, the reviewer faces a strict reality. Optimizing an HPC cluster to achieve a fast solve time is entirely useless if the mathematical output is just numerical garbage. An explicit solver can complete its run without crashing. The resulting 3D animation might even look highly realistic to the human eye, while simultaneously violating the laws of physics under the surface. This chart plots the simulation's energy balance. Reviewers track energy conservation, ensuring the kinetic energy drop exactly matches the internal energy rise, keeping total energy perfectly flat. They monitor metrics. A sudden spike in artificial hourglass energy indicates a Sassine breakdown in physics. Hourglassing is a specific numerical integration failure. It occurs when elements deform into non-physical zigzag shapes that absorb zero energy and offer no resistance. When this happens, the mathematical stiffness dissolves, rendering any calculated stress or strain values entirely meaningless. Reviewers must also execute a gauntlet of other validation checks. They verify physical penetration depths, ensure mass scaling respects strict limits, and scan for unnatural spikes in acceleration data. This rigorous protocol forces the reviewer to cross-examine the animation as a dense numerical experiment, stripping away the visual realism to validate the raw data underneath. True mastery of explicit crash analysis is rarely found in one discipline alone. It exists at the exact intersection of strict structural mechanics, rigorous numerical analysis, and an uncompromising understanding of high-performance computer science.